Hi, I'm Lucy Canick.
And my name is Lucinda Borbash, and we're going to be presenting today our 2019-2020 Ingenuity Research Project on theoretical machine learning, exploring the recursive teaching dimension. So here we have an outline of just what we're going to go through in this project. First, we're going to cover some background on the topic, both on machine learning and our specific topic, the recursive teaching dimension. Then we're going to go through our project, what it is and what it does, and why it's significant. And then we're going to talk about some future work that can be explored with these topics. So first thing, we're going to cover just some background knowledge. What is machine learning? So as we can see here, machine learning is a type of artificial intelligence that allows machines to improve themselves based on experience and feedback. Data security, online search engines, fraud detection, smart cars, and marketing personalization. Every ad that you see on every website you visit is specifically curated for your experience through machine learning. Everything from drones to Siri to Google Maps uses machine learning. It's all around us in our world.
So, if you remember, our project examines the recursive teaching dimension. But in order to understand the recursive teaching dimension, we first need to understand another similar characteristic called the teaching dimension. Given a string from a set C, the teaching dimension is the minimum number of positions required to differentiate that string from all other strings in the set. Essentially, it's a measure of complexity. In the above example, the blue string has a teaching dimension of 1 because there are many ways to differentiate the blue string from the purple string using just one digit. Now, if we consider the recursive teaching dimension. The recursive teaching dimension for a set C is the maximum of the teaching dimensions for each individual string, when the strings are ordered and eliminated in order of complexity. It, like the teaching dimension, measures complexity. However, it gives a better sense of the complexity of the string set as a whole.
So now we face the question, why do we use the recursive teaching dimension? Say you wanted to teach a kindergartner how to do algebra. You could jump right in with the quadratic formula, right in with the hard stuff. After a lot of time and effort, they might get it. However, it would be much easier if you taught the kindergartner how to do arithmetic first. This way, the task of learning algebra is less foreign and difficult because they already know what to do with some of the concepts. The same idea here applies to the recursive teaching dimension. Each string has a teaching dimension, which determines how hard the string itself is to learn. So by separating it into these building blocks, we use the recursive teaching dimension as a way to minimize the complexity of each string, therefore making an entire set a lot easier to learn.
So here's how we calculate the recursive teaching dimension. Bear with us, we'll show you an example in a minute. Given a set of strings C, step 1 is to calculate the teaching dimensions of each individual string. Step 2 is to identify the string with the lowest teaching dimension, record that number, and remove that string from the set. Step 3 is to continue recalculating teaching dimensions and removing strings accordingly until there is only one string remaining. Step 4 is to find the highest of the recorded teaching dimensions. That is the recursive teaching dimension.
In order to make sense of this definition, what we're going to do is we're going to walk ourselves through an example calculation. So here we have a set of 5 strings, string A, B, C, D, and E, and these string names are in yellow. And we also have string positions 1, 2, 3, and 4, and you can see those in dark pink. So as per the method of calculation, what we're first going to do is we're going to organize these strings from least complex to learn to most complex to learn. So here string B is least complex, and string D at the bottom is most complex. So the first thing we're going to do is we're going to learn the least complex string, and that in this case is string B. And if we look at string B, we can learn it with positions 1 and 2. So if you just look at the first 2 positions on each string, string B is the only one with 2 1s there. So if I said to you, hey, can you find me the string with 2 ones in positions 1 and 2, you'd be able to pinpoint string B as the only one with that. In this way, we can learn string B with just these 2 elements. And then, as per, again, the definition, once we've learned string B, we're going to eliminate it from the set. So now we're left with strings A, E, C, and D. And similarly, what we're going to do is we're going to learn the least complex. And now that B is gone, A is the least complex. And we can learn A with positions 2 and 3. Because if you just look at the middle 2 columns, if I said to you, find me the string with a 0 and a 0 in strings 2 and 3, you'd be able to pinpoint string A as the only one with those characteristics. So here again, we can learn string A with positions 2 and 3. And again, this is 2 elements that we take to learn it. And we eliminate string A from our set, and we're left with strings E, C, and D. And now, since E is now the least complex in the set, we learn that one. And we can learn that one with actually just 1 element, column 2. And if we just look at column 2, E has a 1, while C and D both have 0s. So we can distinguish E by this 1 position. And then we are going to eliminate E from our set, leaving us with just C and D. So now we're going to learn string C, and we can learn string C with, again, just 1 element, position number 1. Because C has a 1 and D has a 0, you can distinguish C from D using this position. Then we're going to eliminate C. We're left with just 1 string, and so there's nothing left to learn. So if we look at what it took to learn each string, learning B took 2 elements, learning A took 2 elements, learning E took 1 element, and learning C took 1 element. So as we've defined the recursive teaching dimension as the maximum number of elements it takes to learn any 1 string in our set, when all of them are minimized, that is going to be our recursive teaching dimension. So the maximum out of 2, 2, 1, and 1 is 2, meaning the entire recursive teaching dimension of our entire set is going to be 2.
Especially with large sets, finding the recursive teaching dimension can be a lot of work. That's why we wanted to design a program that would calculate the recursive teaching dimension for you. In order to explain our code to you, we've broken it up into 2 parts, generation and calculation. For the first part of our program, we needed to generate a random set of binary strings. We needed the set to be able to generate as any length or size we wanted, which would allow us to test our calculation code with as many different types of sets as possible. We also needed the strings to be non-repeating, since the recursive teaching dimension is undefined if a set contains multiple of the same strings.
So now that we have our randomly sized and randomly arranged matrix of 0s and 1s that we just generated, we're going to take that generation and use it in our calculation segment. So just like the steps we take to calculate the recursive teaching dimension by hand, we're going to do the exact same thing, but with code, which makes it a lot easier. The first thing that code does is it calculates the teaching dimension of each string individually. And then it takes the string with the smallest teaching dimension, records its teaching dimension, and then removes it from the matrix. This process is repeated again and again and again. And at the end of it all, our code will take the maximum value from the list of every teaching dimension of each individual string. And this value is going to be the recursive teaching dimension of our entire set.
We won't go through all of our code, but we did want to highlight a couple of key points. Firstly, in the left column, we generate an array of unique random strings. This was our generation part. Secondly, this whole middle chunk finds the teaching dimensions of each string in every possible order of complexity that they might generate. This was our calculation part. Thirdly, in the lower left corner, the program finds the maximum of the teaching dimensions, which is equal to the recursive teaching dimension of the set.
So now we come to the golden question. Why does it matter? Why does this matter in our lives? As we saw before, The recursive teaching dimension plays a significant role in the field of machine learning as a whole. Its abilities can help enhance and advance the abilities of machine learning. Knowing the recursive teaching dimension of a data set can help us model that data, sort that data, make inferences from that data, and so much more. It's a lot easier for a machine to perform a task if it knows beforehand how hard that task is going to be. The products of machine learning that we saw, Amazon's recommended for you list, Netflix's percent match rating, they're all increasingly common in our everyday lives. And without the recursive teaching dimension and the other theoretical parts of machine learning, we wouldn't be able to enjoy any of them. So, long story short, if it's significant to machine learning, it's significant to us.
Understanding theoretical components of datasets, like the teaching dimension or the recursive teaching dimension, allows us to better understand the data as a whole, which is always useful. The recursive teaching dimension, specifically, also has increasingly studied relationships with other characteristics, such as the Vapnik-Cherenkis VC dimension. Without going into too much detail, the VC dimension is a theoretical characteristic that allows us to determine how many complete sets of binary possibilities are expressed in a dataset. Like the recursive teaching dimension, it is a measure of complexity. The best way to understand this is through example. Below, on the far left, we have a set of strings, outlined in blue. In the next graphic over, we see that both a 1 and a 0 are represented in the same column in the set. Thus, we say that the set has shattered dimension 1. In other words, it contains all 2 to the power of 1 possibilities. Moving to the right again, we can see that the same is true for all 4 possibilities of length 2. Thus, the second dimension is also shattered. Finally, however, we see that not all 8 possibilities exist that would be needed in order for the set to shatter a third dimension. Therefore, the set has a VC dimension of 2.
This brings us to a discussion of the many possibilities for future work in this field. There are a lot of possibilities just concerning our project, which was examining the recursive teaching dimension through code. This could be bettered by improving our code, making it more efficient, or by examining more or different data characteristics. The VC dimension, like we just explored, is especially promising for a future topic of research because a connection between the VC dimension and the recursive teaching dimension, beyond the fact that they both end in the word dimension, has already been established, but there isn't a lot of work already having been done in a coding setting. So we can see that there are so many possibilities for future work in related fields, related topics. And here are the sources we use for this research. Thank you so much for watching.